Hi, I'm Daniel Chan from UNSW Sydney. Welcome to another adventure in pure mathematics. In this lecture, I want to give you another extremely interesting example where the algebra encoded in the Weyl algebra can tell us a lot about differential equations. And this particular example I want to show you actually comes from the physicist Dirac when he wanted to study the quantum simple harmonic oscillator. Okay, so let's start with the differential equation we want to have a look at. Okay, so the function I guess that one normally want to solve for is psi. Psi is the function of the real variable s here. Okay, and this is, well, up to a small change of variable, essentially the Schrödinger equation corresponding to the classical simple harmonic oscillator. Okay, so we have a constant here, h bar omega on 2. Okay, and then here the equation is you apply this differential operator to psi. Okay, so you get s squared psi of s minus d2 psi ds squared. So we look at this term here. We're going to call it h applied to psi. So h is this differential operator. And we want it to equal this scalar e times psi of s. Okay, so that's the Schrödinger equation in this particular case. And what's the problem that we want to have a look at here? So the problem that we want to have a look at here is simply to find the eigenvalues e. Okay, so there'll be various solutions to psi. Okay, so when we apply this differential operator h to psi, okay, we want to see when is it a scalar multiple of psi and what are those eigenvalues that we get E here, because these eigenvalues will correspond to energy in the physical situation. Now, of course, as a mathematician, if you want to write this down properly and study it properly, you should say where this space of functions psi of s actually lives. We're going to be a little bit sloppy and we're not going to go into the details there. It is important, but I guess the key to note here is that psi should live in some appropriate space of square integrable functions, and also you should be able to talk about the derivatives of them, or the second derivative at least, so there should be a notion of weak derivatives for them as well. Okay, so the reason why I want to ignore it, and this is something of course the physicists often do, but if you want to see how algebra tells you about this, you actually don't need to know where the solutions live. Okay, so the role that algebra plays, for that it's not so important where the psi lives. Okay, so if you happen to know a little bit of physics and want to see more clearly what's the situation, so remember with a simple harmonic oscillator that in the classical case of a simple harmonic oscillator, you want to look essentially at something that's attached to a spring. Okay, so in that case here, the s here essentially is the displacement from the equilibrium position. Okay, and then the potential energy is a constant multiple of s squared. So this is the potential energy term here, and this here is the kinetic energy term. Okay, so if you happen to know a little bit of physics, that's the situation that we're looking at. Okay, so this is essentially the Schrödinger equation, which gives the quantum version of this classical simple harmonic oscillator. Okay, so how do we try to study this? Okay, so I guess the key thing here is that, well, you've got this constant, so let's just ignore the constant part of this first. And essentially, what are you doing to this psi of s? Okay, what differential operator are you applying to it? We're applying s squared minus the square of d ds. Okay, and if you remember back to the first lecture in this, first video in this playlist, one thing that's very key if you want to try to solve differential equations is you try to factorize these differential operators. Now here you think, oh, well, it looks like a difference of two squares. Okay, so if you have a difference of two squares, you know how to factorize that. And that suggests the key notion that we're going to introduce here. So in physics, they're called the creation and the annihilation operators. Okay, so if you have s squared minus something squared, it's the product of the difference and the sum. So what we're going to do is we're going to look at the sum, s plus d ds, and the difference, s minus d ds. Okay, they're both differential operators which live inside the first Weyl algebra, but it will be convenient to just scale them. Okay, so we're going to let a equal 1 on root 2 times the sum, s plus d ds, and a star be 1 on root 2 s minus d ds. And I'll explain to you later why we use the notation star there. Okay, so the first thing, of course, is we want to multiply these two and see whether we do actually get this operator here, h, up to this constant. So let's just see what happens when we multiply those two together. And it's quite interesting, the result. Okay, so we have a star times a, so we're looking at here, this one times this top one, the 1 on root 2 times the 1 on root 2, 1 on root 2, that constant will commute through everything. It's an algebra of the complex numbers, this first file algebra, so we can just multiply the two constants to get half. Okay, so then you'll have an s times this s squared, and that's an s squared that you see here too. Okay, then you'll also have a minus dds times s. And then you'll also have a s times dds. And finally, you'll have minus dds composed with dds, which is the second derivative. So d2 ds squared. Okay, so that's the final thing that you have there. Okay, so let's see. We have two terms which look like what we have over here. You have s squared and then d2 ds squared here. And let's see what happens to the middle term. You'll notice we'll have a commutator between s and dds. And remember, the key relation in the first Weyl algebra is that this commutator, in this case here, is going to give us minus 1. So we'll get s squared minus d2 ds squared. And then these two, when you combine them, they'll simplify to just minus 1. Okay, so we get very close to this operator here, or at least the inside. Okay, s squared minus d2 ds squared. Okay, so something else that will be very important for us is to see what happens when we reverse the order of these two, and we write a star. And we can perform a similar calculation. Okay, so you get the half out the front again, then you have s times s is s squared. Again, you'll get ds times minus dds, so you get minus d squared ds squared. But what happens now is that these two will swap signs. Okay, they'll swap around. Okay, so the commutator will be in the other order. You'll get dds s with a plus sign now, and s times minus dds. So this with a minus sign. So you get the negative of what's here. So instead of a minus sign here, minus 1, okay, you'll get a plus 1. Okay, so the a and the a star do not commute. And in fact, we can say precisely how much they fail to commute by, okay? What's the commutator of a and a star? So that's this one here minus this one here. So of course, these two terms, s squared minus d2 ds squared, they'll cancel. So you get a plus half minus negative half, so that gives you 1. Okay, so this is a key relationship for us as well. The commutator between this a and this a star is equal to 1. Okay, so let's see what the upshot of this is and how these two operators might be helpful for us to look at this Schrodinger equation. Okay, so the first thing is, what is this h? Okay, well, you have this constant here, h bar omega. Okay, oh, by the way, I guess I should explain what these constants are. So h bar is Planck's constant. And when you have a simple harmonic motion, there's a certain angular frequency associated to it that depends on the spring constant and also on the mass of this. Okay, so it's just some sort of constant, and that angular frequency is given by this omega here. Okay, so we have h bar omega, and then half of what's here is basically this expression here. So you have to add 1 to this expression, so you have to add 1 to this n. So this h, this differential operator over here, is going to equal h bar omega times this big N plus 1. Okay. So since there's this very simple relationship between this h and this n here, we know that this operator and this n, they have the same eigenfunctions. Okay. So for example, if when you apply n to this psi, suppose the psi is an eigenfunction with eigenvalue little n here. Okay. Then when you put psi into here, what will you get? Well, basically, since n acts as little n, what you'll get is just h bar omega little n plus 1 times that psi. So that's what h of psi is. H bar omega, the little n plus 1 times that psi. And that's your new eigenvalue. Okay, so in other words, to work out the eigenvalues of this h, and that's our original eigenvalue problem here, what do you need to do? All you need to do is just to work out what's the eigenvalue of this n, this operator here, okay, which we factorize as a star times a, and then work out what they are, that n, and the new eigenvalues are, you add 1 to them, and then multiply by h bar omega. And that's the answer to the problem, modulo finding the eigenvalues of this n. Okay, so let's work out the eigenvalues of this operator n here, which we've written in a factorized form, a star times a. So to begin with, the fact that we'll need is the following, which also tells us why we denote this operator a star, which is 1 over square root s minus d ds, with this notation here, and it's because a and a star are actually adjoints of each other. Okay, so let's see why that's true. And what we'll do is, rather than showing that a and a star are adjoints of each other, we'll just multiply both by root 2. So root 2a and root 2a star are adjoints of each other. So we'll get rid of the constant out the front. So s minus dds is adjoint to s plus dds. Okay, so let's do that. So let's look at the inner product of root 2af with g. So let's apply this root 2a to this f. You'll get sf plus df ds. And you take the inner product with g by multiplying it by the conjugate of g, okay, and integrating from minus infinity to infinity. Okay, so the first part you can write out easily enough is sfg bar ds. That's what you're integrating. And for the next part here, you have this derivative times g bar, and you want to integrate that, so we can integrate that by parts. So let's see what happens when we integrate that by parts. We integrate this one as a factor, so you get f times g bar, and you want to look at the limits from minus infinity to infinity. And then finally you also have the other bit, which comes with a minus sign, and this is the key, the minus sign actually. This is the absolute key which makes this work. Okay, so let's put that in there. You've got the integral of f times the derivative of this g bar. F times dg bar ds ds. Okay, so if you look at this and see what you've got here, okay, so you see that you've got f is here always, okay, so you've got this integral, okay, from minus infinity to infinity. And remember, f and g are square integrable functions, so as you go off to infinity in either direction, it should be 0. So this term here vanishes. Okay, so let's just pull out the common f that you have here. And then what you have for the second bit, well, s is real, so this is s times g bar. You can also write as s, s times g bar, or s times g. And we're going to put a bar over all of this. And then you have here dg ds, and you have the conjugate of that. And that's ds. And if you notice, what is this term underneath this conjugation symbol? This is, you've just applied to this g the operator, the differential operator, s minus dds. And that was our root 2 times a star. So this is equal to the inner product of f with root 2 times a star of g. Okay? So that's why when you take this adjoint, what it does is that essentially the adjoint, this argument using the integration by parts shows you that the adjoint of differentiation is the negative of differentiation. That's the key thing. And the adjoint of multiplying by s, well, that's still multiplying by s. Okay, so that's why this a and this a star are adjoint. And we're going to use that to calculate the eigenvalues of n. Okay, so let's look at this fact here to see how we arrive at the eigenvalues of n. And this is wonderful algebra here. Okay, so suppose we have an eigenfunction psi, and that eigenfunction has eigenvalue lambda. Then the first thing you can say is that the eigenvalues have to be non-negative, so lambda is greater than or equal to 0. And in the special case that it actually equals 0, you can say a little bit more about when that occurs. So of course this just means that n times psi equals 0, but n is a star a, and in fact not only is a star a psi equal to 0, but a times psi is equal to 0. That's the case when that arises. It turns out that if you apply A star to psi, though, this is non-zero. Okay. Okay, so that's the first interesting fact, which tells you some things about the eigenvalues, that they're going to be non-negative. To calculate, to find more information about the values, we're going to have a look at the commutator of this n with A and A star. So the commutator of n with A is equal to A, and the commutator of n with A star is equal to A star. So these are very special types of relationships which occur fairly frequently in mathematics and in representation theory and the theory of differential operators, and it occurs already in this very simple example, which is why I want to show you here. Okay, and the implications are precisely that it's going to really tell us a lot about the eigenvalues of n. Okay, so let me just say what the implications are, and that's in part C here. And that is, okay, so you've got this eigenfunction psi with eigenvalue lambda. Let's apply A and A psi to it. Okay, what happens if you apply apply A and A star to it? A star and A psi now, as long as they're not zero, they will also be eigenfunctions, but the eigenvalue will change. If you apply A star to it, then the eigenvalue gets shifted up by 1 and becomes lambda plus 1. If you apply A to psi, then the eigenvalue will shift down by 1 and it goes to lambda minus 1. Okay, so that's rather nice, okay, that if you have one eigenfunction, you can generate two new eigenfunctions as long as these two are non-zero. Okay, and I've said when this is a 0, this A psi is 0, A star psi is never 0. Okay, you can generate two new eigenfunctions, and their eigenvalues are very simply related to the original. You either add 1 to the eigenvalue or subtract 1. And now finally, we can say what the eigenvalues of n are. Okay, the eigenvalues of n are, in fact, all the natural numbers. Okay, that's all they are. And unfortunately, the argument that I've given here, this is assuming they exist. And of course, remember, we didn't really state precisely what the space of functions we're looking at. So if you pick some very small space of functions, of course, then they won't exist. But as long as you have a reasonable space of functions, then it will be all the natural numbers. Okay, so this is a complete description essentially of the eigenvalues of n, because the natural numbers, and it's gotten purely by the algebra, as we will soon see. Okay, so let's see how that works. So the first part of this fact, to prove this, is that you have non-negative eigenvalues. And that follows from the fact that this is Hermitian. Okay, so let's just see what that means and how that works. So suppose, for example, you look at n psi in a product with psi here. Okay, so what is this equal to? So I guess n psi, this is an eigenvalue with eigenfunction with eigenvalue lambda. So you can, this is just lambda times psi, and you can pull out that lambda. Okay, let's work on this side now. So this n, remember, we factorize as A star A. And now, since A star is the adjunct to A, you can pop this A star to the other side. So that's the inner product of A psi with A psi. Okay, and since you know this is non-negative, okay, and this psi inner product psi is strictly positive because psi is non-zero, that means that lambda has to be greater than or equal to 0. Okay, and when is it equal to 0? The only way this can be equal to be 0 is if this is equal to 0, and the only vector whose inner product with itself is 0 is 0. So that means that A psi equals 0. Okay, so that shows most of this fact, and the only thing I haven't shown here is that A star psi is non-zero. And this actually you can prove in a similar way, because you can reverse the order of these. And remember, the commutator of A and A star is equal to 1. When you reverse the order of this, you actually get n plus 1. Okay, so the eigenvalues of that are now greater than or equal to 1. And since you don't have the case where the eigenvalue of that n plus 1 is equal to 0, you don't get this situation arising. Okay, but I'll let you think through that if you like. Okay, so that's rather interesting. So the fact that we found this factorization, which shows this operator is Hermitian, immediately tells us this fact that the eigenvalues are non-negative. Okay, so the next thing, and this is pure algebra, is to look at the commutator with n and A star. Okay, and we'll just calculate this to show these facts. Okay, so what's the commutator of n and A? Okay, so what's n? n is just a star a. So the commutator is you multiply n with a. That's a star a with a. And then you subtract the product in the other order. So you do a times this n. A times the n, which is a star a. Okay. So what happens here is that, well, you've got a is on the right. You can factor out a on the right. And then you have a star a minus a star, which is a commutator of a star and a. Okay. The commutator of a star and a, and what you will find here is that this is equal to, so what's the commutator of a star and a? This will actually be equal to minus 1. So actually this is minus a, and there should be a minus here, sorry. Okay, so this is going to be minus a. Okay, sorry about that. So that's the commutator that you see there. Okay, so that gives you this, and it's a very similar calculation, allows you to work out what's the commutator of n and a star. And it's going to be plus a star instead of minus there. Okay, so now let's move on to the next part, and I want to say that when you apply these operators a and a star to an eigenfunction, you still get an eigenfunction. And what is that eigenfunction? Okay, so what's n times a psi n? Okay, we want to show that this is an eigenfunction still, so this is a scalar multiple of psi n, a psi n rather, and that scalar multiple is when you apply a, it decreases the eigenvalue by 1, so it should be lambda minus 1 times a psi n. Okay, so let's do that. So what's n times a? Well, the commutator of n and a, so this is n a minus a n. This is going to be equal to minus a, so this is a n minus a. So this is n a is equal to a n minus a psi n, psi rather. n a psi is equal to a n minus psi. A n minus a times psi rather. Okay, so let's have a look at this and see what we get. So firstly we have a n times psi. Now psi is an eigenfunction for n with eigenvalue lambda. So this is equal to a times lambda psi. And then you've also got a minus a psi. So at the end of the day, how many a times psi do you have? This is a scalar, so you can pop it out. You get lambda minus 1 times a psi, okay, which shows you that this a psi is indeed like an eigenfunction, and the eigenvalue, moreover, is equal to lambda minus 1. Okay, so that's what we want to prove about a psi. And that's assuming, of course, a psi is non-zero. Okay. So the other thing that I guess is stated here is that when we apply a star, you get also an eigenfunction, but the eigenvalue now moves up by 1. And to prove that, we use this other commutation relation. The commutator of n and a star is equal to a star. And with the change of sign, that's why you get instead of a lambda minus 1 here, a lambda plus 1. Okay, the lambda plus 1 occurs because of that. Okay, so that's wonderful. Okay, so if you have one eigenvalue, okay, then you get 2 more, lambda plus 1 and lambda minus 1, assuming this condition here, which occurs when the eigenvalue is 0. Okay, so you will get 2 more eigenvalues unless psi was an eigenfunction with eigenvalue 0, in which case you'll only get 1 more, okay, which is the one with 1. Okay, so now we can finally prove part D, which tells us all the eigenvalues of n. And this is, as you can see, it's just going to use pure algebra. Okay, so we're going to find, we're going to consider this eigenfunction psi. Okay, And what we're going to do is we'll also consider the new eigenfunction a psi, unless it's 0, and a squared psi. Since this is an eigenfunction, you can apply again a and get another eigenfunction, unless this is 0. And then you keep going. And what are the eigenvalues? Lambda, lambda minus 1, lambda minus 2, and so forth. Okay? And you keep getting new eigenfunctions unless somewhere along the line you get 0. Okay? So that means what? So that means that, well, if you don't get 0, then you'll eventually get negative eigenvalues. But we said all the eigenvalues, in part A, we said all the eigenvalues have to be non-negative. So that can't happen. So eventually, when you go down, you have to hit 0 by subtracting off some integer. So that means the original eigenvalue had to be an integer. So the first thing you know for sure is that the eigenvalues all have to be integers. So then the next question becomes, well, how do you know that if you have any eigenvalues that you have the set of all integers? Okay, so how do we do that? Okay, well, firstly, suppose you have some eigenvalue, so it's an integer, okay, and then you can get all the smaller integers. How do we get all the larger integers as eigenvalues? Well, all we have to do now is we just apply the a star operator, which gives you a new eigenfunction with an eigenvalue that's 1 bigger. And as we keep applying a star, we get all these new eigenfunctions with these other eigenvalues. So the moral to the story here is really the algebra, what's going on. And the key things here are, firstly, there's this Hermitian operator that's floating around, which gives you non-negative eigenvalues. But the key thing is just these two commutation relations, okay? These two commutation relations basically say that, yeah, when you apply A, okay, A or A star, then the eigen functions get mapped to eigenfunctions, but the eigenvalue shifts either up or down by 1. I hope you enjoyed this adventure in pure mathematics.